Welcome to the workshop. Here is our curious friend Sonu and his mother trying to repair a broken mechanical toy. His mother twists a metallic screw into the toy's joint, but it wobbles loosely and slips right out. She reaches back into the box, selects a second screw, inserts it, and it perfectly locks into place. To the naked eye, both of those screws looked identical. So why did only one of them actually hold the joint together? Relying solely on whole numbers and our everyday eyesight causes mechanical failures. The physical world relies on microscopic, invisible size differences. To keep gears from jamming and fix real-world problems, we have to figure out a precise way to measure the invisible spaces that exist between our standard whole numbers. Let's investigate what happened by placing both screws on a standard metric ruler. This animated diagram of a ruler allows us to zoom intensely into the blank gap exactly between the 2 and 3 centimeter marks. The tip of our first Fulfi screw stretches past the 2 centimeter mark, but it stops in the mysterious, undefined blank space before it reaches 3. We can solve this physical barrier mathematically by splitting that single 1 centimeter gap into 10 equal subtracts. We call each of these smaller pieces a tenth. Counting these tiny tracks measures the exact length of the screw. It lands right on the 7th mark, giving us a mixed fraction of 2 7/10 of a centimeter. Inventing tenths solves our first measurement problem. But what do we do when a physical object is so small that it lands between these new tenths? Let's step into this crisp, sterile paper folding lab to test an even higher level of mathematical precision. Here is the challenge. Take a strip of paper measuring exactly 8 9/10 units long and fold it in half to find its midpoint. This diagram shows the breakdown. The 8 whole units split cleanly into 2 groups of 4. But when we try to divide those 9/10 in half, we find ourselves stuck between the marks. Laying the folded paper back on a scale reveals the problem up close. The edge is trapped in a tiny blank space. It sits past 4 4/10, but it hasn't reached 4 5/10. To fix this, we need a secondary mathematical solution. We slice a single tenth into 10 smaller microlines. By doing this across the whole ruler, we divide the original whole unit into 100 equal pieces, called a hundredth. Now we can state the exact measurement of the paper's folded edge. It is 4 whole units, 4 tenths, and exactly 5 hundredths, written as 4 45 hundredths. Whenever we hit a measurement barrier in the physical world, dividing a subunit into an even smaller subunit allows us to map the physical world with increasing precision. This diagram shows the downward ladder of fractional scales we just built, starting from whole units, stepping down to tenths, and finally down to hundredths. This precision is why the second screw Sonu's mother found actually worked. When engineers can measure in hundredths, they ensure that every gear, bolt, and joint fits exactly as intended, preventing the kind of wobbling and slipping Sonu just witnessed. But this creates a final practical problem. Writing out massive fractional block equations every single time takes far too long for engineers working on paper. Let's take this problem to the holographic chalkboard for a textbook challenge straight from the grand mathematician. This chalkboard diagram outlines your specific numerical challenge. Group these fractional blocks together to find the total value of 87 ones, 5 tenths, and 60 hundredths. Combine these values, work out the final number, and drop your answer in the comment section below. Next time in episode 2, we will unleash the magic separator, a cleaner, faster way to write these precise measurements using a single dot.